Hello everyone, a warm welcome to the fifth day of 7th E-School on Climate Science and Policy. We hope you found yesterday's lecture by Professor Rangan Banerjee on Economics of Climate Change insightful. Those who could not attend the previous sessions can find the lectures on YouTube channel. Kindly ask your questions in the link provided below in the description, YouTube description. Today we have with us Professor Pradip Kalbar. Pradip Kalbar was awarded PhD in Environmental Science and Engineering from Indian Institute of Technology, Bombay. Presently, he works as an assistant professor at the Center of Urban Science and Engineering at IIT Bombay. Prior to joining IIT Bombay as faculty, Pradip worked for 2 years as postdoctoral researcher at the Technical University of Denmark. The postdoctoral fellowship was awarded under HC Ostad Postdoc Fellowship Program, co-funded by Marie Curie Actions Program of EU. He has received prestigious awards such as Excellence in PhD Thesis Award 2014 from IIT Bombay, Young Faculty Award 2016 IIT Bombay, Prisma Sustainability Assessment and Policy Award 2020. His area of research includes water supply, wastewater treatment, life cycle assessment, circular economy, and climate change mitigation. He will be discussing about the topic climate change mitigation role of life cycle thinking today. Over to you, sir. We welcome you to
Yeah,
the
thank you.
e-school.
Yeah, thank you, Sindhuja. Thanks for the nice introduction, and welcome participants to this series of e-school. So, just I'll share my screen. Yeah, so basically, I'm going to talk about climate change mitigation, role of life cycle thinking. I am Pradip Kalbar. I work at the Center of Urban Science and Engineering, IIT Bombay, and I'm associated faculty of interdisciplinary program in climate studies. And we have very good group here in IDP climate studies, working on various topics related with climate studies. All aspects such as science, policy, adaptation, mitigation are covered. And in this school, you'll be exposed to uh, different these aspects of climate studies. So today I'm going to talk specifically climate change mitigation and what is the role of climate change mitigation and how life cycle thinking will help in addressing the climate change mitigation. So it will be a very overview of life cycle thinking. I will not able to go in very much details, but idea is to at least expose you with the concepts, key terminologies, and I will demonstrate one international case and one Indian case of applying life cycle thinking for developing climate change mitigation strategies. So basically, my research areas are urban water supply, wastewater management, climate change mitigation, and sustainability assessment. And this I work in primarily in CUs and in IDP climate studies. So today's talk is going to cover these two aspects of climate change mitigation and how further we can do the overall sustainability assessment. That's I'm going to demonstrate through with some cases. So, so why basically climate change mitigation or overall sustainability debate? And you must have been exposed to many of this particular sustainability and climate change related concept. But if you have observed the this particular graph from 1900 to 2010, so we particularly we have been posing a lot of pressure on environment in terms of extraction of raw materials. For example, extraction of construction materials grew by a factor of 34, and this is globally I'm talking about. So extraction of ores and minerals grew by a factor of 27. Extraction of fossil fuels grew by a factor of 12. Extraction of biomass grew by a factor of 3.6. So this is the data about the raw material extraction, and this will have impact on all sorts of indicators such as climate change, water, and everything. So particularly today we are going to focus only on climate change. Okay. So this is the global trend of GHG emissions in 2010. This is the most updated data that is from uh, AR5 from IPCC report, and you can see that mostly the CO2 from fossil fuel and industrial processes is causing the main problem. So you can see the CO2 fossil and industrial processes are causing large global GHG emissions. And then there are other greenhouse gases also contributing. So this is a trend. So total around 49, about 49 gigatons every year GHG emissions is happening. Then if you go from a total to regional data, that which regions are emitting more, and you can see this particular data where OECD countries are basically major contributor. Then Asia is joining the particularly in this contribution. So all developed countries are already ahead in GHG emissions. And then here we have the per capita data. So this is the world average, about 6 to 7 per capita emissions ton CO2 equivalent per capita per year. And other countries like OECD developed countries are here, and Asia is here. But slowly, like in India, we are also having development happening. So slowly, everyone will join there if we have not done something drastically change in our way we use resources, technological improvements, and lifestyle changes. So that's what I'm going to discuss today. This is the sectoral picture of this 49 gigatons, whatever number is that, of and which are the sectors. And you can see the energy itself is causing around 25%. Then you have the industry, then you have transport and buildings. So and inside that also buildings itself are consuming energy. So these are the some major industries need to be focused, and some interventions should be prioritized in these sectors. So then we always take a representative concentration pathways, and I think you have already must be introduced by previous speakers in this series about RCP scenarios from IPCC reports. So representative is for possible future emissions and concentration scenarios. So basically, IPCC has evaluated thousands of scenarios, and then they have suggested a few representative concentration pathways. And the trajectory of the pathway is the trajectory of greenhouse gas concentration over a time to reach a particular radiative forcing at 2100. So uh, basically, these are the thousands of scenarios that have been assessed, and you can read the IPCC report for further further of your interest. But you can see here that most possible and conservative is here RCP 2.6, which leads to around 2 degrees Celsius temperature. And basically, we have to limit the growth such that we have to be below 2 degrees Celsius target. That means in 2050, in 2050, the temperature change should not be more than 2 degrees Celsius. So, and then there are further assessment. If you trace from this graph about uh, how much temperature change will happen for given concentration of GHG emissions, here the concentrations are given, you can estimate the budget, carbon budget for globe. So basically, from this IPCC report and then the special report in 2018, we can come up with the budget which is has a basically 1600 gigatons CO2 equivalent global budget. That is available. That means that we can emit this much of uh, GHG emissions up to 2050. So that is 2 degrees Celsius target. And then there is another very restrictive 1.5 degrees Celsius target, which really reduce even in half degree, because if you have to remain below 1.5 degrees Celsius, 860 gigatons CO2 equivalent. So more realistic scenario is 2 degrees Celsius. Even I'm saying realistic, I'll show you some numbers which shows that even in remaining in 1600 gigatons CO2 equivalent will be a big challenge. So because 1600 gigatons CO2 equivalent for entire globe, and then you have to divided by population, if you are going by per capita, and then you can estimate how much CO2 equivalent you can emit per capita per year in a given country. Okay, that's how you can estimate the budget for individual country. So this is the budget you can see here, carbon budget as per RCP 2.6, that is gigaton CO2. So India can emit this particular total 7.16 gigaton CO2 emissions, and then this is the per capita per year ton CO2 right now. So you can multiply by the population and see where we are there. So basically, there is a growth that is happening every year in the CO2 emissions, because we are developing. We need to use energy. We need to use resources for providing basic amenities and facilities to the mass of the population. So that's why our emissions are going to be in a rising trend. So we have to do things differently if we have to limit the uh, carbon CO2 emissions in a given budget. So this is the top emitters in the so this is world, rest of world, and China, USA, EU 28 countries, and India. So you can see that steadily these particular emissions are increasing for from 2000 to 2018. So and this is the per capita CO2 emissions for again this regional for these regions. So world, rest of the world, China, USA, EU, and India. So you can see there is a 4% growth in last about one decade, and this is the budget that is available. Like every person on in the world can emit 5.24 tons per capita per year if we have to remain in RCP 2.6 budget. Okay, so this is the scenario we are talking about that, and if we maintain this growth, then we will also soon join China or other developed countries. So we have to change our production processes and lifestyles if we have to remain below this particular budget. So there have been many international deliberations and commitments by various countries. So one of these is intended nationally determined contributions coming out from Paris Agreement 2015. So 148 out of 196 participated nations submitted their intended nationally determined contributions. So INDC highlights domestic measures to fulfill Paris Agreement. Okay, so every country is now who has agreed has some basically agreement. So India's goal is to reduce the emissions intensity of its GDP by 33 to 35% by 2030 from 2005 level. Okay, so that is the commitment we have. Now the challenge is how we can do this. So we need a lot of changes to bring in for meeting this INDC. For example, we have to make our transportation efficient. We have to reduce building energy, and so many other strategies we have to apply. So that's where the role of climate change mitigation comes in picture. So climate change mitigation refers to efforts to reduce or prevent emissions of greenhouse gases. So there are different efforts we can do, and mitigation for simply can mean using new technologies and renewable energies, making older equipment more energy efficient, or changing management practices or consumer behavior. So it can mean various things, and we have to identify these mitigation strategies, prioritize these mitigation strategies, and that's where I'm coming to focus that what are these, how we can prioritize these mitigation strategies. Basically, you may have multiple options and you may want to choose, okay, which one I should start. That's where the life cycle thinking role comes in picture. So hope I am clear about what is the background I am building this particular lecture. So uh, basically, then there is a decoupling challenge that is proposed in United Nations Environmental Program. So decoupling challenges, on x-axis you have the time intensity, and in time, and on y-axis you have the intensity of resources or quality of life. So as you can see, after industrialization, 1950s and 60s, human well-being are is improving, whereas use of nature is decreasing. Okay, so we have done the development, but by the use of nature. So, and you can see the economy. These are just notional graphs to propose a decoupling challenge. So, issue is now if we have to fix this use of nature, means we have extracted the raw materials, we are using the fossil fuels, creating the climate change impact and all sorts of impacts. If we have to fix this graph, that means you have to decouple the growth from use of nature. Okay. So how we can do that? So at least this graph should remain straight, the use of nature, that we have to see. So that can be done using some strategies such as, for example, we have to do change in production. So change in production means we can improve the particular technology, and that particular energy consumption can be reduced. For example, take an example of television set. That television sets in 1980s and 90s were having cathode ray technology, so they used to consume more energy. Now, with the advancement of technology, you have flat screens and LCD and LED technology, which has a reduced energy consumption, but that is per unit. But if you take the sectoral picture, that for that particular sector, whether the emissions from that sector have reduced, the answer is no. The emissions are not reduced for that particular sector because the consumption has increased, because you are giving a more efficient technology which is more cheaper, and our population is exploding, our lifestyles are changing, so people are more consuming the TV more. The per unit TV units sold in India have drastically increased. Now in the higher income groups, people have more than one television set in house. Number of hours of watching television has increased. So this has all caused to more consumption. So it is, so don't assume that technology efficiency will always make the environment better, because there are rebound effects. So in sustainability science we call it as rebound effect. So there is always a rebound effect to any technology that you can that is given to the society. For example, car mileage. So more efficient car you give, assuming that it will save the energy, what will happen is that people will start consuming more. So because the efficiency is more, you can drive more in a one given amount of petrol or diesel, people will travel more. So that is the rebound effect. So we have to have some policy fix also when you give a particular technology to the society. So this particular sustainability science is closely related with the people's behavior. How people are going to use the technology is a very difficult to predict. So we have to be careful of. So that's where the some these tools and techniques I'm going to talk, which will assess the impact. So the only change in production is not going to help. We have to bring change in consumption and production simultaneously. That means we improve the technology, and we also make sure that people are changing their lifestyles. Okay. So one of the studies I'm going to demonstrate, where it shows that only change in technological efficiency will not help. We have to have some change in the lifestyles. Okay. So the first goal then remains is to devise strategies for such decoupling and climate change mitigation. There is a need for estimation of environmental footprint of consumption components. Okay, so you have to uh, uh, estimate the environmental footprint of option A and option B, alternative A and alternative B, or project A or project B. Then only you can decide which is better for environment. Okay. And as I said, the complexity of environmental problems are uh, like rebound effects are there, and there are so many societal considerations we have to do. The path towards estimation of environmental footprint needs a very holistic approach. Okay. So that's what is needed. If you if you want to estimate the environmental footprint, we need a holistic tool, and some of the tools I will introduce in this particular talk. So many approaches are used for assessing environmental performance of products and services. So uh, for example, material flow analysis, you can do a very simple material flow balance. How many materials is going in a particular product or particular area, but that doesn't account upstream and downstream resources or impact. So you have to take a life cycle perspective to account upstream and downstream. So it's a very good starting point, MFA, but doesn't give a complete idea of environmental footprint. You can also use some energy-based indicators such as energy assessment methods to take more comprehensive approach. So carbon footprints, water footprint, energy indicators are also can be used. But all that have the lacuna at that those the account do not account upstream and downstream impacts. So we have a holistic tool such as lifecycle assessment, which takes into account all upstream and downstream. So I will introduce you to these particular tools in a brief, and then I will move on to the case studies. So, MFA, very briefly, I will tell you about MFA. So, MFA is a systematic assessment of the flows and stocks of materials within a system defined in space and time. So, basically, you have to define the space and time. For example, a city, and let's say period of 1 year, how much plastic is going in and how much plastic is going out, or how much water is going in and how much water is coming out. So, that kind of balance MFA can allow you to do. Very simple example, it can be given. So this is called Sankey representation. These diagrams are called as Sankey representation. Very nice for giving you the idea. So basically, this is the representation of, let's say you have a heap of a municipal solid waste, or let's say 1 ton of municipal solid waste, that is mass. Okay, when it is scientifically burned, or it is called incineration, when you do the incineration of municipal solid waste, what happens is 70% of the mass goes as off gas. uh, there is 25% in the bottom ash and 2.5% in the fly ash. Okay, so what is happening here is you have a bifurcation of the flows. So that is the preliminary picture. Let's say your aim is to just trace cadmium, or the heavy metals in the flow. Uh, so the cadmium goes 92% of the cadmium available in this particular 1 ton of municipal solid waste goes in fly ash. Okay, so the entire picture changes here. So what is observation? That MFA can give you a very good idea to start the investigation in the environmental hotspots. That which are the streams are focused for your your investigation. Okay, so if your aim is that to check only the heavy metal emitted from this incineration, then you have to just focus on fly ash, because everything is going in fly ash. Okay, all the cadmium properties of the heavy metals having properties of cadmium are going by this fly ash. So this is one example. The another example is that you can take a particular uh, let's say country, and this is, let's say, plastic flow in a given country. So you can map that how much imports happening tons per year, production happening tons per year, distribution, consumption, and stock, and then there is a export also. So after you consume, there is a waste generation which is going in the collection, and something is going to the stock. Stock is that, let's say, the plastic will remain in the household for more than 5 years or 10 years. For example, furnitures or some other items, those will remain there. So that stock is released after some 20 and 25 years. So everything is collected, and that is, some part is recycled and some part is disposed of. Okay, so this is very simple diagram you can create using tools available, and there are free tools and commercial tools both available. Then you can make it more complicated, and this is very nice work by Lu et al. Group in 2009, where it is a global anthropogenic metallurgical aluminum cycle, which shows that what is happening to aluminium in globally. Okay, so for example, how to read this graph is, here the units written, that if it is a stock, it is million tons per uh, million tons, and if it is a flow, it is million tons per year. Okay, so you have the reserves, aluminium reserves, 7,000 million tons. Out of that, mining, refining, smelting, casting, semi manufacturing, manufacturing, and use in various sectors. For example, building and construction, transport, automobiles, packaging cans, various sectors are there, electrical cables. So those are consume the aluminium, and large part of it is, again, the post consumer scrap goes back to the remelting and refining. And about 4.7, you can see here, 4.7 uh, uh, million tons per year goes in municipal landfill. That is not recoverable. So that particular uh, mass is completely lost to the waste. Okay, so this is the global picture. So this is very nice learnings you can draw from material flow analysis than directly jumping for a more comprehensive or a more complicated analysis uh, to just understand your system. So what is important is to understand the flows, elementary flows in your system, and then you can jump to a more complicated analysis. So you have the material flow analysis, carbon footprints, and many other uh, tools. Then still, why we need a LCA? Because LCA provides you a holistic picture, that is life cycle perspective. I will introduce you to the life cycle perspective in some time. Then it internalizes the externalities. So externalities, that something is not accounted in your system boundary. So it allows you to expand the system boundary and take into account everything. It is a best measure for eco-efficiency. And remember, circularity means resource efficiency may not be always eco-efficient. So you can, so it means too much of recycling may not also be eco-efficient. So you have to do it by case basis. And LCA allows you to account for local as well as global impacts. Okay, so for example, local impacts such as eutrophication, soil pollution, those are accounted, as well as global impacts such as climate change, ozone depletion. Those are also accounted simultaneously. So basically, environmental science and engineering problems are very interdisciplinary complex, and that's why we have to have such a comprehensive approach. And lifecycle assessment is a methodological framework for estimating and assessing the environmental impacts attributable to the life cycle of a product. Okay, so I will just introduce you to the perspective life cycle assessment. So this is the let's say you have the production phase comprised of raw materials, material processing, and assembly, which uses materials and energy. uh, for every box you can see here there is a material and energy, and then there is a waste stream. So material and energy and waste stream, material and energy. So for raw material acquisition, material processing, manufacturing, assembly, everything you have to account in the production phase. You have to account everything in the use phase, that whatever energy consumption happening, whatever the waste generated during the use phase, that you have to account. And then you have to also account everything, retirement and recovery and treatment and disposal. So this entire particular thing is called life cycle perspective. Okay, so that you account the production phase, use phase, end of life phase, that is life cycle assessment. So inside this, reuse may happen, that something is used in the system boundary, something is remanufactured, that you fix the washing machine, or you fix something and refurbish and send it back for consumer. Then there can be a closed loop recycling, meaning that, let's say, aluminum for cans can be collected separately, and those can be recycled back in a metal processing facility. And then you can basically have the open loop recycling, where everything is mixed, that all sorts of waste are mixed and taken for recycling, that is open loop recycling. So this all you need to account. So you have to take a life cycle perspective, you have to account for all sorts of reuse and recycle and remanufacturing, and then study the system's impact, overall impact. Okay, so what is the benefit of doing this is that many times there may be a burden shifting. Okay, so some product, they may use some material which may reduce the energy consumption during the use phase, but that material may be toxic. Okay, so that material, when the product is disposed of, for example, some battery, if somebody invents some battery which is very efficient and consumes less energy, and if it is disposed of, then it creates a lot of toxicity. Okay, so that in sustainability science we call as burden shifting, that companies can basically tweak the design, so some pollution can be passed to the next phase, which is not their direct responsibility. Okay, so that is called burden shifting. So you can by basically pass on your climate impacts to other phase, and then companies can claim, oh, then this is not in our scope. So life cycle assessment avoids that particular burden shifting, because now everything is included. So the complete life cycle assessment accounts for production phase, use phase, and end of life phase. Okay, so this is basically avoided. So basically, burden shifting is accounted into the life cycle assessment. So this is the framework, because the previous slide shows a very comprehensive picture, but then many universities and researchers have come up with the different approaches to do life cycle assessment. Then that's why the ISO has come up with the principles and frameworks for for life cycle assessment. And there are mainly four phases: basically goal definition, scope definition, inventory analysis, impact assessment. So these are the uh, goal definition, scope definition, inventory, impact assessment, and then you have to interpret the results. Okay, so interpretation is the most important part. So many times I see people conduct LCA, but interpretation is not done properly. And based on your interpretation, you have to conclude, specify the limitations, and then make the recommendations. And the use of LCA can be product development, strategic planning, public policy making, and marketing. Okay, so so how it is operationalized? So this is the operational framework of life cycle assessment, that you define a goal and scope. For example, goal can be to compare two product, or you can set a goal as that you just want to uh, uh, improve your product. You don't want to compare with any other company or any other product. You just want to improve your products. How we can replace the material which are not causing climate change or not causing toxicity or any other impacts. That can be the investigation question. So goal and scope is defined in accordingly. And then there is a inventory analysis. Okay, that you collect all the data, technical inputs and outputs, emissions, resource use, and everything. And then you have the life cycle impacts. Okay, so you collect this particular data, and there are so many life cycle impact indicators, as you can see here: climate change, ozone depletion, toxicity and ecotoxicity, eutrophication, acidification, land stage. So, and there are so many models available in the life cycle assessment softwares. So those life cycle impact assessment methods are available. Those will link or transform inventory into life cycle impact assessment. So, and there can be various different types of LCAs: product level LCA, organizational LCA, consumer lifestyle LCA, or you can compare country A with country B. So there are various of these types of LCA are possible. And these terminologies you should remember when you talk about life cycle thinking, that when a company does a impact assessment study inside the boundaries of the company, that gate to gate, that some company manufactures some product, they will just declare the impact of the production. Okay, they do not give the impact what about the material from where it is extracted, or where what will happen to the product after manufacturing. That is gate to gate impact assessment. Then you have the cradle to gate, that companies will account for everything, that from where the raw material is extracted, what is happening to the raw material, the impacts during the production phase, up to the gate of the company, that after the product is dispatched for the distribution, they do not account it further. Okay, that is beyond their control, or they don't want to account for various reasons. Okay, and then there is a cradle to grave, that companies will cover everything, that from product extraction, material production, assembly, retail use, and end of life. Okay, everything is accounted. So ideal picture is that you should have a cradle to grave, but because of various reasons, responsibilities, data availability, the LCA may not be accounting cradle to grave, but maybe gate to gate, or cradle to gate, or gate to gate grave, whatever it may be the case. But you should remember this particular case, the terminologies. So the first part that is more important in life cycle thinking is the functional unit. Functional unit is how you compare the products, okay, or the services. That everything is very different. Like, can you compare apple versus oranges? So you initially will say no, but in reality, you have to compare. If you want to, let's say, choose a fruit for your nutrition requirement for a period of 1 year, so you have to change the problem, pose the problem in a way that the products are transformed into services. Okay, so functional unit represents what service being delivered by the product, that and enables different systems to be treated as functional equivalent. So what is the functional equivalence between two fruits. Okay, it can be nutrition comparison, it can be vitamins comparison, it can be calories comparison. So you have to bring out that aspect of the comparison for the life cycle assessment. Okay, so you cannot compare fruit on kg to kg basis or dozen to dozen basis. That is the principle. You have to fix your functional requirement, what functional requirement you are looking at. Okay, so and function the functional unit can be have primary products can have primary functions and secondary. For example, fruit, the primary purpose may be the hunger, but the secondary purpose may be nutrition or vice versa. Or the shirt, for example, have the primary function to is protection from the weather, but the secondary purpose is aesthetics and lifestyle, and so many other things can be there. You have to define what you're going to account in your study. Okay, the basic functional, the primary function fulfilled by the product system has to be declared. Okay, so and this quantifies the service delivered by the product system. So service meaning that I wear a shirt which is a product A, but that lasts for 5 years and allows me to protect from the weather for 5 years. So that is the service offered by the shirt for next 5 years. Okay, so this is the way you think in life cycle assessment. Okay, that you convert the product into life in the service. For example, shirt example I have given you, that uh, for example there can be two options, that high quality shirt and low quality shirt. Okay, and the functional unit in this case is that shirt for protection from weather and privacy for 5 years. So that is your primary function. Now we are not talking about the aesthetic and the lifestyle or any other. So this is our primary functional unit. And here you can see that you cannot compare this product based on case to case, that you cannot compare one product with another product directly, because one shirt may last for uh, 5 years of time, or it may last for 1 year of time if it is a low quality shirt. Okay, so that's how you account everything in the system by applying life cycle thinking. And it becomes more complicated, that if you want to compare the paints used for the homes, so you cannot compare 1 liter of paint to another 1 liter of paint, or 1 kg of paint with another 1 kg of paint, because the surface area that is covered per kg or per liter vary, and the paint that will last for number of years will also vary. Okay, so the comparison unit can be x meter square area to be protected for y number of years. Okay, so that can be the comparison unit for paints. And there can be more complicated examples. For example, this, if you want to compare CFL with incandescent bulb, you can those who are interested can think of what kind of functional unit you can use uh, for this kind of products. So this you can take it as an home assignment, those who are interested. Then there is a system boundary, that you have to define the system boundary. That once you define the goal of the study, there can be a technical system boundary, that what kind of technologies are involved, geographical system boundary, what is the geographical scope you're talking about, and the temporal system boundary, that technology of what year, because every now and then technology gets updated, the efficiency changes. So energy production efficiency in today's time and 10 years before is different. So you have to define the system boundary, and that influences the result of LCA. Okay, and hence has to be defined with the in LCA and declared in the methodology section, that what is your goal of the study, what is the system boundary. Everything has to be declared in the methodology when you do carbon footprint or any other assessment using life cycle thinking. Everything has to be documented in the uh, methodology document. So mostly this is the picture where you can think that what are the things that you have to consider. So this is the foreground system, that means actual manufacturing is happening here. This is the foreground system. And but there are so many supporting upstream systems, such as you need a water, you need a steam, you need a electricity, you need so many other elementary flows, raw materials to manufacture. Okay, those are upstreams. And then the manufacturing unit manufactures the product and creates some waste that goes in the downstream and creates the products which are sent out for the users. So you can see how the technosphere interacts with the ecosphere, that it extracts the resources and it emits out the wastes to the ecosphere again. Okay, so this is the you have to remember that we operate in a foregone system, that you just see the manufacturing, but to manufacture something, so many other resources, so many other elementary flows are required that are very essential. uh, so this is the example of product system of life cycle assessment. So you account for elementary flows, then you and there is a transport, production, energy supply. For example, elementary flows can be crude oil from ground and solar radiation, or elementary flows such as emissions to air, discharges to water and or soil and radiation. So this can be the overall picture. And this is the unit process, that is the heart of the life cycle inventory, that you have to account for every process. What are the raw materials are going in, what is the energy, water, air, land, ancillary materials going in, and what is coming out from the system, from the given unit process. Okay, and that data is available in LCA softwares, and that's why it becomes a very very comprehensive process to apply or conduct LCA. uh, so you have to quantify all these arrows from input side and output sides to start the LCA. So if some process is not available in the database, you have to go and collect the data from the field and do this particular analysis. For a very simplified example is given here, that a unit of toaster, the toast maker that we use for the breakfast, let's say, so it's produced using 1 kg of steel and zero point 0.5 megajoule of steam, and then it's used for 1,000 times and then disposed of. That is the life cycle of a toaster. Okay, so you need a steel, you need a steam, and for steel, 1 kg CO2 emissions per kg of steel. Just for example, it is given 4 kg CO2 per megajoules steam. That is the emissions of CO2, and this is production, this is use, and this is dispose. Okay, so this is because it is 0.001 kg. So energy used during the toasting is contributing this CO2 emissions. You can see that this is multiplied by 1,000 because it is used for 1,000 times. So cumulatively, you can see this is 6.5 kg CO2 for a life cycle of a toaster. That is how you think in a very very simplistic manner. Real life is a very different. What happens in real life is that steel is required in a steam manufacturing and steam is required in steel manufacturing. Okay, and that you cannot do solve this problem in a straightforward manner as this particular algebraic sum. You need a matrix combinations. Okay, so you have to do matrix inversions and then solve this particular problem. So that's why you need a software or a excel spreadsheet to do a more complicated life cycle assessment. Very simply, very briefly I explained, and it's you have to explore in a more deeper manner if you have to understand, but I'll just explain you with some simple example. And once you do this with the inventory and everything, you come up with this kind of inventory, that how much emissions of pollutants are happening. Okay, that is, this number is generated for every kind of pollutant, and that is transformed into life cycle impacts. Okay, and this particular arrow is, these calculations are done by software in the behind, and that that all impact assessment methods are developed by various research groups. So you have to choose the particular impact assessment method, and that gives you the global warming potential, ozone depletion, and so many other impacts. And you have this for product A and product B, and these are the different impacts for product A and product B. So these are the impacts, and you can go through later for this. But climate change, ozone depletion, toxicity, acidification, those so many impacts you can account, and there are so many models that are embedded in the softwares before. So you are not doing the actual impact assessment calculations; those are there in the software. You are just multiplying the inventory data with the with the characterization factors, and you are seeing the impacts. Okay. So, but remember that lot of research and models are already there in the software, which are basically which will help you out do the impact assessment. So this is the inventory results. This is elementary flows that are coming. Then you transform them into midpoint impacts. So midpoint meaning these are the potential, that climate change potential, ozone depletion potential, human toxicity potential. This is the potentials of impacts. That is not actual damages, because there is a climate change potential, but actual damage is depending on the where this particular impacts are going to happen, whether it is in Mumbai or whether it is in some desert. Then the impacts are different, like human life loss will be different if it is a highly dense area, whether it is a desert. Then diversity loss, toxicity impacts, everything will be depending on the region. And that's why you need another phase of impact assessment called endpoint, or area protection, that we call. There is human health, natural environment, and natural resources. So these are the transformations that happens in life cycle perspective. And you can further do aggregation of single score, because policymakers will finally say, okay, everything is fine, but tell me a final score, which on which I can choose strategy 1 or strategy 2, or product A or product B. But it's, although policymakers wants to have a single score, but you have to remember that level of uncertainty increases as you do a high level aggregation. Okay, and in one of the studies I have proven the drawbacks of single scores, how much uncertainty it adds and how much bias it can be. Because right now everything is uh, uh, highly influenced by climate change impacts, because all these models are complete more comprehensively for climate change, but other models are not that much evolved, toxicity and acidification and eutrophication. So basically, the single score are highly will correlate very well with the climate change impacts in the current scenario. So this is just developing area, so particularly life cycle assessment, uh, and how you do interpretation. That is bigger question. Okay, that you do this all the things I have said, and then you have the let's say alternative A and alternative 2, and you do the life cycle impact assessment, and you have come up with global warming potential and toxicity. So just observe these two impacts, and you can see this is the raw materials impact, manufacturing impact, packaging, transport use, and end of life. So what is happening here is, uh, observe the trade-off. That product A is good in basically toxicity, but bad in global warming potential. But product this alternative two is bad in toxicity and good in GWP, climate change potential. So there is a trade-off. So still, if you do the life cycle assessment, the problem is not solved, because there are alternative which are performing differently in a different impact category. So you need to process these impacts, and there are various methods such as multi-criteria decision making which can be used to process these impacts further. Okay, so this needs further processing. So the entire point of this is, what is the role of life cycle thinking. So I will take a break here, and let me know if there are if I'm going fast, or if there is a so you can chat. You can put a chat in the chat box. I can see the chat box. It is. Is it going well? I'm because after this I'm going to talk about some case studies, because in a shorter time I'm trying to cover much of the material. Okay, so I'm hearing some comments. Okay, so this is the background of methodology development. Okay, that is very complicated. You will not understand in one shot. I will show you some applications in whatever time remaining. Okay, so the role of life cycle thinking is that analyze the system from life cycle perspective. Okay, that is the first group role. You can choose all or one indicator, for example, climate carbon footprint, or climate change potential, or GWP, whatever you want to call, and compare the estimated value of indicator for your system with available budget. So I said in the initial that you can fix the carbon budget for a given community or per capita, and then trace the impact of that particular per capita impact to the available budget. So you can know if this is the budget, how far I have to go to not to exceed this budget. Okay, what kind of technology efficiency, what kind of lifestyle changes I have to do. Okay, so evaluate and prioritize the mitigation strategies. So using this methodology, you can evaluate and prioritize the mitigation strategies. So one of the such studies we have conducted for Denmark. So first I will explain the Danish case, and then I will come to the Indian case. So this particular study we conducted for what is the impact of urban Danish resident. Uh, that was the aim of the study, and whether it is what kind of strategies, mitigation strategies, will be helpful for limiting the climate change impact into the Danish environment. Okay, so and these are the publications are there, so you can refer. You can write to me if you need the copy of these publications. So the we applied the life cycle assessment coupled with the personal metabolism. That is the term we coined. So we did there was collaboration from University of Aarhus, and they had this data from different people. We processed the data. What data comprises of the accommodation, thermal energy, electricity, transport, and food of 1281 Danish urban Danish citizens. Okay, so what is the area that is they are living, what is the thermal energy, what is the electricity, what is the transport, and what are the food that they are consuming. Okay, and this is we called as personal metabolism model. That is what person is consuming in a 1 year of time. Okay, that is the metabolism that is happening, and what is the waste that is being generated. So we model the impacts of these four sectors using Gabi software, using Ecoinvent 2.2 database, because this work is 2015 and 16 when I was a postdoc in DTU Denmark. And then we had a SEMA Pro for just released 3.1 version available for food impacts. Okay, and then we coupled this to complete the life cycle assessment. So we had the combined life cycle assessment impact assessment results for both midpoint and endpoint level. So this is the outcome. It's very comprehensive. In one slide, I'm trying to show you what is this. Don't get confused about this graph. Very simple. This is I'll explain. So you can see the climate change, agriculture, land occupation, fossil depletion, freshwater ecotoxicity. These are the impacts which are there coming out from life cycle assessment. Okay, you can just focus on climate change, which shows that it is contributed equally by all the sectors. What are the sectors? 1, 2, 3, 4, 5, 6: accommodation, heat, electricity, road transport, air travel, and food. So earlier we thought it's the energy consumption must be dominating the climate change impact, but this is the first study which showed that climate change is equally contributed by all of these sectors. Okay, and this study had a very great influence on Danish policy as well. So basically, what you can see here is this is whereas toxicity impacts you can see are dominated by food. Okay, it is very clear that every so this whatever you are seeing here on the y-axis, these are 1281 Danish citizens impact plotted on one shot. Okay, and these are the climate change impacts that you can see here. So all agricultural land occupation, freshwater ecotoxicity, these are basically dominated by food, but climate change is dominated equally by all these sectors. So message is, if you have to control your climate change potential, you have to act on all sectors simultaneously. Okay, that was the one policy suggestions this study gave. The next question that we addressed is better but good enough. That there can be some strategies for technology improvements, but the question is whether can the Danish environmental impacts can be held in a given budget of 1.5 or 2 degrees Celsius target. So the question that in the next study we addressed is, can foreseeable efficiency improvements of technologies and conceivable changes allows the developed nation to make its fair contribution to global climate change. Okay, and this is the publication that we have. We can go through. If you need a copy, write to me. That whether pursuing necessary reductions in embedded GHG emissions of developed nations will efficiency improvements and changes in consumption get there. Okay, because as I said, only efficiency improvement is not helpful. You have to do the changes in consumption. So this is the methodology followed. That first we estimated the carbon footprint of all the Danish citizens. Then we conducted the emissions and had some scenarios that what happens if people stop flying, what happens if people go for a vegetarian diet, what happens with people start sharing the accommodation, and then finally how far they have to go to control the CO2 emissions in a per household. So 2014 to 2050, if they have to reduce the uh, carbon emissions, by what factor it has to be reduced? That are the questions we addressed in this study. So I will not focus more on this, because this is Danish case, and these are the results which shows uh, what happens to the CO2 emissions for these. These are the 1281 Danish citizens data, which is plotted here. Okay, and these are the scenarios, that what happens if the everyone remains on the same lifestyle, that is this scenario. What happens if there is a increase or decrease, or no car or airplane or meat? Okay, these are the scenarios that we have modeled. So even if the people do this, no car, airplane or meat, uh, still the budget available for Danish citizens is 2 tons per CO2 equivalent per capita. Whereas even if people stop using car, airplanes, and non-veg diet, their emissions still remains higher, uh, 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 about 5.5 or 6. So it's a very drastic lifestyle change is needed to fit the Danish GHG emissions, if 2 tons CO2 per capita is adopted budget for the policy making. So this is how you use the life cycle thinking for devising the strategies for climate change mitigation. So the same same methodology can be used for technology selection. So earlier I given you the international case of uh, uh, basically uh, life cycle impact assessment. Here I'm going to give you how you can choose the technologies. Okay, so in India, we have to fulfill the sewage treatment generation and treatment gap. So basically, we have the lot of sewage generation, but there are not installed capacities. So government of India is planning to uh, basically install many wastewater treatment plants. But if the technology is not correct, then we will have the problem. So how we can use life cycle thinking for selecting the technology which has a lower climate impacts or and other impacts. That's how I'm going to show you. So these are the some technologies: activated sludge process, sequencing batch reactor, and so many technologies are available. And this is like sequencing batch reactor, ASP, MBR, USB, and FL, constructed wetlands. And the technology selection can be based on what is the end use of the treatment system. Okay, whether it is for land irrigation or disposal, or whether it is for recycling, that can be the deciding factor. So based on that, we develop a framework. We take an active sludge process as one example from a real life plant in Pune. Then we take the USB FL from Nasik. That is another technology. Don't go into details of technology, those who are not from wastewater treatment sector. Just see how we can apply life cycle thinking. Then we chose another very different technique, like constructed wetland. So you can imagine we're comparing very different technologies based on life cycle thinking. So it is really comparing apple versus oranges. Okay, this constructed wetland is look like this is the technology. Okay, this is land based, plant based. One photograph I shown is completely equipment based and energy based. So there is a sequencing batch reactor, and when you do the impact assessment, you come up with this kind of results, that you have the acidification potential, global warming potential, eutrophication potential, and other toxicity impacts. What life cycle things allows you is to basically see here the GW potential is negative for constructed wetlands. Okay, so this is because you have the uh, basically plants are basically absorbing the CO2 while they are doing the growth. So climate change mitigation is happening with the treatment itself. So whatever plants this, so life cycle thinking allowed to capture the CO2 that is fixed in this particular biomass. Okay, and that is reflected here in this negative. All other technologies are giving you positive impacts on climate change, whereas constructed wetland, which do not need energy to the for operation, but it allows you to actually fix the carbon and help you in the climate change mitigation. That's how the climate life cycle thinking helps you for uh, uh, for developing any decision support. So I think I will stop here, and we can have a more discussion, because in a very short time I try to give you various frameworks and impact assessment methodologies and life cycle thinking, and then I have shown you very quickly two cases. This was just purpose was to give you the overview of the work, and a lot of details goes into, and you may have a lot of questions, but you can read the papers that I have, and if you don't have access, write to me. I'll be happy to share. Yeah, thank you. So we can start Q&A session, Sindhuja. Back to you.
Hello, sir.
Yeah,
We got few questions from the viewers. Shall we display the questions on the screen for you?
yeah,
Can you see the question?
yeah. This cradle to cradle approach, and will climate adaptation measures have life cycle thinking? Yeah. So cradle to uh, cradle to cradle is basically you completely create a ecosystem where everything is utilized there itself. So cradle to grave means you take and you dispose, and everything is accounted. Cradle to cradle is that everything is recycled, but that is over recycling also sometimes. So you may have to transport a lot of material from one place to another place, and that may cause huge transportation impacts. Okay, so you have to be careful. But for a smaller place, if you decide, okay, for this particular village we will not go out of this system boundary, and everything is produced is again given back to the to the same area, same geographical area. So that is called cradle to cradle, and there is a cradle to cradle certification also available, C2C certification. So life cycle thinking C2C certifications are there. And the second part is, will climate adaptation measures have life cycle thinking? Yeah, means you can apply logical thinking for choosing the best climate adaptation measure. Okay, that whether to go for a strategy A or strategy B or option A or option B, it depends on you whether you apply life cycle thinking or whether you apply only carbon footprint, conventional carbon footprint. But ISO, as per ISO that is dedicated for carbon footprint, dictates that you should have a life cycle thinking applying carbon footprint. So it's up to you. My message is that whatever method you apply, you should declare it in a methodology document. Okay, and be transparent about it. What is the approach, scientific approach that you are taking? Okay. Yeah, next question. Why one more LCA is required if some data is available by IPCC or other? Can we quote the same figures? uh, So IPCC, so if the study is taking some approach which is suitable for you, for example, you do not have to account for all life cycle impact. See, it's all user driven. LCA is not mandatory; it's a voluntary tool. First of all, okay. Environmental impact assessment is a legally binding tool in India right now, and LCA global is a voluntary tool. You don't have to do LCA, and also it takes a lot of time and effort and data collection and resources also. So if you are not required to do LCA, it's fine. But ideally, uh, life cycle assessment is the most holistic approach to start with. And if the IPCC data, whatever impacts you have, those are just emissions, emissions. And if those are taken from life cycle perspective, it's fine. You can use them. You don't have to do LC again. Yeah, next question. While doing LCA of a product which includes a main and a byproduct, since both of them have been produced by a single energy source, should we consider? Yeah, so this is the biggest. It's a good question. Uh, I have not covered in this class the methodological details of LCA. Okay, the question that is asked is, while doing LCA, some process may have two products. One is the main product and one is byproduct. For example, take an example of agriculture land. Let's say you have soybean. Okay, and you have the soybean land of 1 acre. So you get a soybean beans and you take a oil, and that is your product. Byproduct is the basically biomass that remains in the agricultural land, which may have some value, right? Or the rice, you extract the rice, but you have the rice husk, which may have some value. How you allocate the impacts between these two product, main product and byproduct, and there are a lot of scientific debate about it, and there are various uh, models that are used and various principles that can be used. What can be the principles? Such as mass. You can bifurcate the impact by mass, but that can be the injustifiable in case of, for example, agriculture case of rice. So rice, if you div- uh, so you have the mass of the rice husk, and you have the mass of the rice that is produced. So you may, if you want to divide the impacts based on the mass, then uh, uh, rice husk weight might be little bit significant. So you may end up getting allocating more impacts to the rice husk. But you can use, let's say, economic principle also, the price of the product. So rice itself will have a very high price than the rice husk, so automatically all the impacts will be will be sent to uh, rice. Okay, but these are then energy based, or it's any other volume based, any other principle you can use. But allocation is a really unresolved question, and but economic allocation is also used. Economic allocation doesn't ascertain you the mass balance of the system, because you are going by price, then mass balance disturbs. So but you then mass balance, if you go, then you're not really valuing the actual product, and the impact should go to the actual product. So there is a lot of debate about it. Ideally you can do 2 3 allocation methods and see what is the sensitivity of those impact assessment methods. Yeah. Next question. How can we estimate GHG emissions during municipal wastewater treatment process based on SBR technology? Do these gases significantly contribute to global warming? So basically, uh, you can account the emissions from not only SBR but any other technology, wastewater treatment technology, because a lot of energy goes in wastewater treatment, and it's significant, not as significant as other in other sectors. But if you just focus on water as a sector, energy that goes into the wastewater treatment sector is huge. Okay, that these all, if you visit any wastewater treatment plant, you can see a lot of many equipments are operating, blowers are pumping air into the reactor, and that consumes a lot of energy. And in India, energy is around 60% is derived from fossil fuel, so that will have the impacts. Okay, so this particular definitely can be accounted, and that's why I was showing in a very short case that you can account emissions as well, and fixing of CO2 also, if the plant-based technologies are used. Okay, the phytoremediation based technologies are used, and these gases significantly is a very I think tricky word. How much significantly? Because right now in India only 37% of the wastewater generated is treated. If you have 100% wastewater treatment, then significant amount of emissions will occur from this sector. Yeah. Next question. Can the life cycle approach be adopted in case of ongoing development projects? You can. Means it again. It's a voluntary approach. EIA is a mandatory approach. See, LCA is one of the tools that can be embedded as part of EIA. So EIA, as a EIA practitioner, you can use a life cycle assessment for estimating the impacts. Right now, the EIA experts might be using some other models, some other methodologies. They can adopt LCA and do the EIA. And during the development project, yes, let's say there is a development project, and you want to know what are the best way to operate the particular system, so that combinations can be worked out and then energy can be saved. Yeah, LCA can be used. Yes. Next question. How do the EIA of large dams in Tehri Dam in Uttarakhand? Yeah, means it is EIA itself, the framework and the way it is conducted, it's itself different topic. I don't know, means this session was not intended for that, but EIA itself has a process, the scope definition and data collection, and then you do the impact assessment, biodiversity loss, or greenhouse gas emissions. Those are different methods and models can be used. So there is a standard process of EIA of in India that is carried out, but the methodologically it's various models can be applied. So I don't know what exactly user is trying to say, but you can refer to any other EIA talk lecture, and there this is commonly discussed how to conduct EIA of any hydroelectric project or large dam like Tehri Dam. What will be the impact on life cycle analysis used in Indian policy making with respect to the draft EIA nation? Uh, so means uh, you can, as I said, LCA can be recommended as one of the tool for conducting impact assessment, because if you do the conventional assessment, let's say you do carbon footprint without taking into life cycle perspective, you end up not accounting something. So the new draft EI notification can include life cycle assessment as one of the methodology, but again, it has to be voluntary. India is not ready to go for full-fledged life cycle assessment. Reason, we don't have that much database. In European countries, database are available for each and every process in the software, so you just have to collect very little primary data, and that's why you can see a lot of research is happening in Europe. For example, the Danish case that I shown from Denmark, I could do it in 2 years because that all data was available, and only modeling part and the interpretation part was required. Okay, so that once you have the data, then you can do the LCA very not easily, but the job becomes simple. If you have to collect the data from scratch, it's very difficult. So in India, we have to first develop a database, inventory database. So I just don't want to link initially this EIA with LCA. We have to separately work for LCA, collect the data, develop the inventories, submit that inventories to the EcoInvent. EcoInvent is a large database service provider from Switzerland, and that gives freely for academic institutions. So that process has to be started first from the ministry and academic institutions. Then once the database is ready, then people can use it for EIA during the in the process of EIA. Okay, so just don't immediately link LCA with EIA. That will, unnecessarily cause a trouble to the crack practitioners. That if they, I come across some case that people are asking to conduct LCA, but India, when there is no data available, because everything is connected in economy. That every product is manufactured, the raw material is manufactured somewhere, transported and again manufactured and then distributed. So that kind of database we don't have right now. Okay. Yeah. Next question. Again, EIL related question. Do you think community reserve forest should be included in EIA policy to mitigate climate change? Uh, I think I will defer this question because this is really related to EIA. And EIA policy is, again, there is a draft notification and it's developing. So the impacts can be accounted, and if but there are a lot of different practices happen around community reserve forest that I've come across. So it's a really debatable topic. Right now, I don't want to give any opinion about this. Okay, so just pose questions related to life cycle thinking. How to integrate solar, hydro, wind, battery storage plants in LCA? So we basically in LCA, as I said, the primary processes of all this energy production. For example, 1 megajoule of energy production from solar, 1 megajoule of energy production for hydro or wind. Those all have to be first fixed, collected data, and those unit processes has to be available in the database. And then you can, for a given region, for example, in Maharashtra, for a given grid, you can generate a mix of all this, so we call it as energy mix. So you have to create a process which will give you the impact for a given energy mix. So whatever energy mix Maharashtra has, so you have to combine these different processes and take fractional, that if 64% is a fossil thermal, and 64% impacts will be contributed from fossil fuel. If 5% is solar, that much impact will be accounted. So that's how we integrate into LCA. Okay, that is called energy mix methodology. Is there a study done using LC theory for renewable energy tech? Yeah, there are many. Means there are many studies which are done for renewable energy technologies for solar impact, for solar parks, for wind energy. If you just search a literature on Scholar or Scopus, you can find. But that is more in European context. Again, in India, there is no database for life cycle assessment. So those studies. So in my research group, we are doing very small scale uh, life cycle based carbon footprinting impacts. Okay, not all the impacts are possible. So it is just a emerging field still. Means my PhD was in 2008, and that time I applied LCA. Whatever result I showed for wastewater treatment plant, that way from 2010 and 11, and still we do not have the database required for conducting full-fledged LCA. So you can imagine the challenge, because the data available from the industries, hosting it to some platform is not happening. Ministry and government has to take some action, and there are some discussions going on, but we have some other priorities right now, like implementing the available rules and regulations, and then going to the LCA. Okay, so there are uh, 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 challenges related to applying LCA in India, for at least for emerging or the advanced technologies. Yeah, next question.
These are all the questions, Professor. Hello.
Yeah, thank you. Thank you. Yeah.
Thank you, Professor. Thank you for the lecture. Shall we wait for more questions, or shall we go ahead?
Yeah, we have time. So if someone has questions, please put up quickly.
Um, I think these are all the questions. We can finish the
You can
session
write
if
to
you.
me. Yeah, you can write to me. Okay. So I'll just in the chat box I will give my email ID. And if you want any publication or any questions, you can write to me.
Thank you, Professor. I'd like to thank all the team members, Shravani and Shiba. Um, and a special thanks to Nikita, a PhD student of Professor Kalbar, for helping us out today. Um, we will end the session. So there's a new question. Shall we look at the question?
I can see how does the biodiversity affect on mitigation measures. Uh, how does the biodiversity affect mitigation measures? Uh, can you elaborate the question, please?
Um,
Can you elaborate the question, please, Mr. Adit Dev? What exactly you are trying to say? I don't get. Yeah, you can. Yeah. So I think I will.
we will end.
Yeah, you can write to me. Yeah, no problem.
Thank you, everyone. We'll see you tomorrow for the next session. Thank you, sir.
Thank you. Okay, so elaboration has come. Is it challenging to adopt the biodiversity to create the mitigation techniques? Is it challenging to adopt biodiversity to create? Is it challenging to adopt the biodiversity? Again, I'm not getting what you are directing. Maybe you can write to me, okay, and we can discuss. But overall, I think you are talking about uh, any see maintaining biodiversity will overall help in any kind of impact, whether it is climate change mitigation or any other. But I'm not able to get your exact question. But you can write to me in a more detailed manner, and we'll take from there. Okay, thank you.
Thank you, sir. Uh, Hello.